So, as we said, liquids and solids wouldn't exist without intermolecular forces. In liquids, there's two things that happen that are due to the result of intermolecular forces, and those are surface tension and viscosity. You can get a paper clip or a needle to float on the surface of water, which seems like it should be impossible, right? Because metals are more dense than water and they tend to sink, right? So how can you float a paper clip on water? Well, it's due to something called surface tension. If you look closely at this picture, you can see that the surface of the water seems to sort of be bent, almost like there was a skin or a tarp over the top of this, like a pool cover, and the paper clip was sitting on top of that. That skin on the water is called surface tension, and it is the tendency of liquids to minimize their surface area. The paper clip will float on water. It won't float on gasoline or alcohol because those substances have lower surface tension and it's not enough to support the weight of the paper clip. So here's an illustration of the water. Inside the water, the molecules are interacting with, in this two-dimensional representation, 6 different neighbors. On the surface, this molecule interacts only with 4 neighbors. This results in a net inward force that creates tension at the surface and resists penetration. Because in order to break into the surface of the water, you have to push apart the particles. The ones on the interior have more connections. When you break into the surface, you increase the surface area, and so you're going to cause more molecules to have 4 interactions instead of 6. Those are not actual numbers, but in the illustration. So to push into the surface of the water, you need to create more surface area. The water doesn't want to do that because it'll result in breaking attractions. Does that make sense? Water drops are spherical because of surface tension. When we observe water like dripping from a faucet or from a leaf or from your nose when you get out of the swimming pool, it has a teardrop shape. That's because gravity is pulling down on it. But if you, like this one right here, it's got a teardrop shape. If you look at water in space where there's no gravity pulling on it, we see that it forms a sphere. Now, if it's been disturbed at all, it'll kind of jiggle and wobble a little bit, but undisturbed, it wants to be a perfect sphere. A sphere is the shape that has the smallest surface area per unit volume. Viscosity is how thick a liquid is. It's the resistance of a liquid to flow. So which pours more easily, honey or water? Water does. Water is less viscous than honey. Honey has higher viscosity. It doesn't pour well. And that's because the interactions between the molecules in honey are stronger. In order for a liquid to be fluid, it has to be able to move. The particles have to move relative to each other. That involves breaking interactions and making new ones. When the viscosity is high, when those interactions are strong, it's a little harder to break them. It still happens, it will flow, but it flows more slowly. That's higher viscosity. That makes me hungry. Maple syrup poured onto a stack of pancakes. It flows slowly because of the viscosity. The molecules, I kind of think of intermolecular forces like being Velcro. So here you've got the particles in something that's viscous have fairly strong Velcro. And you can imagine if you are wearing a Velcro suit and someone else is wearing a Velcro suit and you're trying to pass each other in a small, constricted area, you're going to kind of stick to each other. Can you get past? Sure, you're not going to be locked to that person forever, but it's going to be harder than if you're like wearing Teflon suits or something and you're just going to slide right past. That make sense? Or corduroy versus silk, or I don't know.